there no questions? So can someone summarize what was covered in the previous class? If there are no questions, then you're perfectly clear, right, as to what was covered. Krishnakant, can you summarize what was covered in at least one point? Yeah, so what are the differences?
One is mass point, one is based on mass point theory. The whole mass is concentrated in single point.
Yeah.
And other, it considers differential mass and the total force is something on the
Body. Yeah. So then, any other point of difference between the mass point mechanics and the continuum mechanics? The definition of body itself is he's covered that partly. Mass is concentrated at one point, whereas the body in the continuum mechanics is regarded as a collection of material points. Right? So what about the equation of motion? Mass is not a variable. Mass is conserved. Controlled volume mass is variable. For the body, the mass is not a variable. Yeah. So control volume we are not getting into now. Any other fundamental points of difference? How would the equation of motion? So we looked at basically the mass point mechanics, we write for short as MEM, and the continuum mechanics, we write as CM. So one thing that's been pointed out is the body and the mass of the body, right? So the body is simply a point and mass is concentrated at a point, or is assumed to be concentrated at a point. So that's the mass point. That's why it is covered. The continuum, the body also has fixed mass. The body is a collection of material points of fixed mass the mass here is actually continuously distributed in volume with respect to volume. The meaning of that is this is what gives rise to the notion of a mass density, rho, right? So here we could write the fixed mass is given of the body is given by the integral of the density distribution, right, over the volume that the body occupies. So the body is at some location at some time t, right, and it goes, let's say, to another location at some time t plus delta t. So this is the same body, same collection of material points. The density distribution will be different in the two cases in general. Some special cases where the density remains the same. But for general, the density distribution over the volumes that the body occupies could vary, right, as the body moves in space and time, but the mass remains fixed. We're dealing with the same collection of material points. That's the identity we assign to the body. Same collection of material points being followed in motion, right? So another way of looking at it is how you define the density. Is basically we assume that this kind of a limit exists. Let's say I fix a point, then I can consider a certain mass of fluid around it, right? A volume around that point. Now this volume has a certain mass, so we could call it, let's say, delta M, and let's say this is the volume that I assume is delta V, right? So I take any point in the fluid, I consider a small volume, a region surrounding the fluid. You have a certain volume, you have a certain mass. I can take the ratio of the mass to volume. So basically a continuous distribution of mass means that as I now shrink this volume towards that point, as I keep on shrinking, the limit of this as delta V goes to 0 is what we take as the density, that the limit exists, we assume, right? And that would be the limit, and and that would give rise to the notion of the mass density. That's written here in integral form in this way, right? So that's another way of writing that. So now, with regard to the equation of motion itself, the well-known equation of motion, the Newton's second law, is force equal to mass times acceleration. If I were to write this or extend this to be applicable to fluid mechanics or continuum mechanics, then I have to apply this law to a differential element of fluid, because as we pointed out, the body as a whole in continuum mechanics doesn't have a single acceleration, because each of the material points are moving with their own velocity and acceleration, right? So we can apply the Newton's second law directly only to a differential element of mass, and we say that the differential force acting on the differential element is given by the mass times the acceleration. Can you please open the door? Thanks. There's another way of writing this in mass point mechanics, and that is F written as the time rate of change of the momentum of the body, right? Force written as time rate of change of the momentum. Now this has an analogy in continuum mechanics too. And without proof, I give sort of a plausible proof for this. We formally write this in a better way later, with proper explanation of the derivative, the substantial derivative that I introduced, right? So the force acting on the body again is given by the time rate of change, right, of the momentum of the body. So now we can associate a momentum of the body even in continuum mechanics, right, of the body as a whole. So the momentum is given by the integral of the mass density times the velocity, each of which could be in general changing with from point to point at a given instant in that volume that the body occupies, right? So I have to integrate the momentum density over the whole volume, then I get the momentum of the body. If you see the units of rho v dv, this is the volume, it has the units of momentum. So we get again the time rate of change of momentum. But if you want to follow the body, then you have to introduce what is called as the substantial derivative, which I will formally define later, right? So now if you see here, often in continuum mechanics we will be dealing with densities more often than the actual mass. We will be dealing with what are known as local equations of motion. So we call the density, here is the density of mass. This is the density of the momentum, so density in the sense of per unit volume, right? So that's the momentum density. When that is integrated over the whole volume, we get the momentum of the body as a whole. So rho is a mass density and rho times v is a momentum density. We generalize the equation of motion to continuum mechanics. The point, as I said, was that the nature of the forces in continuum mechanics has to be further established, and that was finally done by Cauchy. And in continuum mechanics, we need to consider two kinds of forces. So one is the body force, and another is what is called as the contact force. Right? So the body force has its analogy in mass point mechanics, as it is sometimes called an action at a distance type of force. Forces due to gravity or various other fields like electromagnetic fields and so on. But if we were to write it properly here, now we deal largely with continuum mechanics alone. This is a fairly general way of writing the equation of motion, the integral equation of motion. Right? Or you can say this is the generalization of Newton's second law to deal with bodies such as fluids in motion. Right? So this will be Fb plus Fc, and Fb is typically written as like this, which I now explain. These are the two kinds of forces. Unfortunately, in notation, this is the stress vector. This is not to be confused with the time. Maybe I'll try to slightly tilt it. That's a scalar, the time. What I've written here as T with the vector underscore is the stress vector. So these are the two kinds of forces acting on a body. So I'm focusing on a particular instant of time. This is what I have associated as the body. It has a certain mass, fixed mass, right? Now what this rule says is that if I want to calculate the time rate of change of the momentum, right? So I consider the momentum of the body as a whole at time t. I have to calculate the time rate of change of that momentum. And Newton's law says that this time rate of change of momentum is equal to the net forces acting on the body. We have to explicitly consider two types of forces, the body force and what is called as the contact force, the surface force. If you look at the body force, it's an integral over the volume occupied by the body at time t. Right? So to calculate the body force, I need to know at every point the value of the density, mass density, and also the value of the body force, which B is clearly the body force per unit mass. It's a vector, right? So B is the body force per unit mass. This is again like a force density. That's only one part of the total force. The body force per unit mass. A crucial distinction between the body force and the surface force is that the body force requires a specification of the body force density at every point within the volume occupied by the body. If you look at the way the contact force is written, that's why it's often referred to as the surface force. It is still acting on the body, it's not just acting on the surface, right? To calculate this contact force, I need to specify, because this is an integral over the area or the surface bounding the volume, or the surface that is enclosing this body at time t. So this is the area. So element here would be dA. So dA is an elemental area on the surface of the enclosure that is surrounding the body at time t. Right? So that is the stress. This is the T is the stress vector. Now it depends. It has to be now specified at every point on the surface. In contrast to the body force density, this is also a density, but it has units of force per unit area rather than per unit mass or unit volume. Right? This is also force density. Right? So stress is often referred to as force per unit area, right? So it has the same units as force per unit area. It has to be specified though at every point on the surface that is enclosing the body at time t. So it can vary with the position on the surface. It will of course also be dependent on the particular instant of time that I am focusing on. Now on top of it, the most important point here is that it also depends on the quantity n. That's also a vector. Can you guess what the n could be? The unit normal vector, right, which gives effectively the orientation of the area element. So if I have an elemental area here, the outward normal is often referred to, because when you talk of a normal, it can be outward or inward, both are normals. The direction is the same. I mean, the line along which they are acting is the same. The direction will be different because depending on which you choose, and it's typically convention to choose n to be the outward normal. It effectively gives the orientation of the surface. This is effectively due to Cauchy, who said that this is the most general formulation of the contact force in continuum mechanics, or at least one of the most general formulations. important point here is that the t vector, the stress vector, depends not only on the position and time, but also the orientation of the surface. Understanding this is very important in fluid mechanics, right? So now, how did he arrive at this? I mean, why do you need to propose that actually the contact force has to depend on the normal? Precursor to this is the hydrostatic force or the pressure force, right? In hydrostatics, pressure. We talk of pressure, the notion of pressure in hydrostatics. Different interpretations were given to the pressure. For instance, we all know that if in the common way of dealing with pressure in hydrostatics, we have, let's say, water in a container, and let's say this is the pressure E naught, and this is the pressure at let's say a location H below is given by E naught plus rho G H. Right? This is in hydrostatics. The pressure is sometimes regarded as the weight of the fluid acting at a particular point. That's one way of looking at pressure. Pressure, the meaning, is actually coming from the first part of the word press. Fluid elements pressing against each other. It dates back to time of Archimedes, who dealt largely with hydrostatics. The fluid elements pressing against each other. That's the contact force. As I pointed out yesterday, the contact force is arising out of the fluid being in contact with other parts of the fluid. That is, the body force is like an action at a distance. It is arising even though it's not arising out of any contact. It's just effectively a distance based on an action at a distance force. Right? So this is one way of looking at the pressure, but the generalization of the notion of pressure as a field of vectors was due to Euler. So basically Euler said in hydrostatics first, the pressure is actually written as a vector. Right? So there's always a question, what is the stress? If you say it is force per unit area, since force has the units of vector, you could call the stress as a vector. Right? The pressure is at a scalar, we take P equal to nRT by B. We are treating it as a scalar. Right? So pressure is also a scalar, it can also be a vector, or regarded as a vector, depending on the context. So Euler proposed that, but he was the one who introduced this kind of a free body diagram, where he said that rather than regarding the limited view of just looking at it as the weight of fluid, he simply isolated a body of fluid, let us say in hydrostatics, even a fluid at rest, and he talked about what are the forces acting on this body of fluid. Right? So he said the pressure force, the force due to the pressure, is given by a field of vectors acting on the area bounding the particular volume of fluid. Right? It is to be specified all around the surface bounding a particular body of fluid. So the pressure force is defined in this way. Okay, so what does this mean? This means that the pressure is acting all along the normal. So it acts as a minus times n. So the direction, this P is a scalar. So if you're asking whether pressure is a scalar or not, pressure has a vector. Pressure also has a scalar part to it. This is the scalar part. This whole thing is a vector part. So Euler proposed the pressure is always acting in the direction of the normal in hydrostatics. We now know that that is true. That is taken as a rule. Actually, it's a correct interpretation of the forces acting on a fluid at rest. That is hydrostatics, right? So it's always acting along the normal. It has a negative sign because we said the normal is outward. So if you now consider this as a fluid at rest, let us say, right? So the pressure is acting, it's a pressing force. The outer fluid is pressing against this body of fluid that I am now focusing on, right? So it is acting in the direction opposite to the outward normal. And further, it is given by, you also would have read, the pressure is the same in all directions. So what does that mean, right? That is given by this. This is the scalar. That is the same in all directions means. So suppose I take a point here. So this is a location x, and in hydrostatics we don't need to deal with time, right? So it's a location x. Now this is one surface that is passing through that point. So the time can actually be suppressed. Right? Just explain that. So this is one surface. I can have another surface of fluid passing through the same point. So that at that same point, this will have a different orientation. Let's call this n prime, right? But what this rule says, let's suppress the time because we're dealing only with hydrostatics now, right? What this rule says is that the magnitude of the pressure will be the same because we're dealing with the same point, but a surface which has a different orientation from the original surface that we consider, right? That is what is meant by pressure is same in all directions. So no matter whatever be the area element, the orientation of the area element that you consider at that point, the magnitude of the pressure will be the same. Depending on the orientation of the element, the direction of the pressure will be different and will be acting along the normal. Now, or for want of anything else, assume this for fluids in motion also. So in which case that the scalar could depend on time also. So if you adopt this view, now also this is regarded as valid, but only for a special class of fluids called the perfect fluid. If you take this rule, the pressure is same in all directions, but the contact force is same in all directions, it acts always along the normal. If you carry it over to fluid mechanics, it's not valid in general for a fluid in motion, but it may be regarded as a good approximation for certain fluids which could approximate as what is called as a perfect fluid, right? So that is the idea. So Cauchy said he relaxed both of this assumption, but in general, now you can see that this force is dependent on xp as well as n, but it has a very special form, right? Cauchy said the special form need not go within a body in motion, with a fluid in motion, but rather you just leave it generally. It could depend on the position, the time, and the normal, right? So you just leave it like that. That's the most general formulation. The idea for that certainly came from Euler's work on hydrostatics, which he later generalized to hydrodynamics, right? So that is the origin of that. So having done all this is still not complete, but this sort of completes the introduction that I wanted to give for this course, right? So we have seen how the notion of the body, the distribution of mass, the equation of motion, the nature of forces, all of those ideas had to be introduced to finally arrive at a proper description for a fluid in motion. Are there any questions at this point?
So, if the stress vector is a function of all those three elements, then what about the body force? Is it a function of just time?
Body force density is a function of, this is also a function of, I didn't write all the, this is in general would be a function of position and time. So there are two important distinctions between the body force density and the contact force density. One is that the body force density, if I want to calculate the force acting on a body, the body force density has to be specified at every point inside the volume occupied by the body. And it's dependent only on the position and time in general, right? But the contact force density, which is given by this quantity, first it has to be specified not within the volume of the body, but along the surface that is enclosing the body at any given time, right? At every point of the surface you have to specify it. On top of it, the distinction is that it's dependent not only on the position on the surface and the time, the particular instant of time and time, but also dependent on the orientation of the area element at that point. Yes?
So isn't the stress a tensor?
No, this is a stress vector, right? So we haven't yet introduced a stress tensor. That's the next part that we'll cover when we go to the post proper. So the point here is that now this says how this pressure vector is dependent on the orientation. It's simply directly proportional to the orientation. Now the next question is, if you generalize this and say that it need not act on the normal or along the normal in the general case of a fluid in motion, then how does it depend on the normal? That problem had to be solved. That is what points is indicating of the greatness of the work of Cauchy, because he solved that problem also. That I will just give you the final answer that he solved in the following way. We now derive this formally later. He said that this is equal to the normal times the stress tensor. This is a dot product of a vector times a tensor. This is what leads to the stress tensor. It is just a 3x3 matrix for all practical purposes, and this, even though it's written in the form of a dot product of a vector and a tensor, it is nothing but the multiplication of the vector with a matrix, right? So all this says is, this is n1, n2, n3 times, this is a, what is this? This is a,
Symmetric.
it's not a symmetric, it's just a row vector, right? So it's a 1 by 3 matrix, right? So actually, this is transpose, transpose, because normally when I write vectors in terms of the components, I write it in column form, right? So this would be, I can write this as E1, E2, E3. This would be row, because this is 1 by 3, this is 3 by 3, and the net result will again be 1 by 3. And these are the components of the stress tensor. So the stress, there is a vector corresponding to the stress, there is also a tensor corresponding to the second order tensor. You will have 9 components. For all practical purposes, if you are scared of the word tensor, right, you can just regard it as a 3 by 3 matrix, because all the tensors will be dealing with predominantly will be second order tensors, and you can just regard it as a 3 by 3 matrix for all practical purposes. So this is what it is. So this is very important. This resolution of the way the general stress vector depends on the normal is very important, because if you look at this equation, right, you look at the stress vector, the complication that arises when, because it is dependent on both x as well as n at a given instant of time, you have to see how complicated that would make it. Because what this means is that now suppose I consider a particular point, right? Now I'm not worried so much about the body, but I'm worried about the specification of the stress vector. What do I need to know, right? So let us say I consider a point. This is all at a time t. So I consider a point within the fluid. Now I consider one surface passing through that point. As I pointed out, if I consider another surface, right? Now the orientation of that will be different. So I can consider two surfaces. One is n, another, let's say n prime, another is n double prime. At the same point and the same time. So I consider two different surfaces passing through that point. What this says is that the stress vector, right, is very different for the two different orientations at the same point at the same instant of time. So I can consider the infinite number of surfaces passing through that point, and for all of them, I am considering infinite. For each one of them, the stress vector will be different. That is what the proposal says. Right? So what this means that if you want to specify the state of stress at a particular point in space and at a particular instant of time, I have to provide an infinite number of stress vectors to completely calculate, because I could consider any surface passing through that point. I want to know what is the stress vector at that point, right? So, since I can consider an infinite number of surfaces passing through that point, that means there are infinite number of orientations possible at a particular point. So, there are infinite number of stress vectors that I have to specify, right? But what the Cauchy's theorem basically says, by resolving the way the stress vector depends on the normal, it says that I need to specify only 9 components of a stress tensor, and then you tell me what the orientation of the surface is at that point. I will tell you what the stress vector is. So it reduces the problem of having to specify an infinite number of stress vectors to merely specifying the 9 components of the stress tensor, because this is independent of the normal. So the normal dependence is separated out, right? So all I need to specify is T11 of xt. This is all dependent on. So now at a particular point and a particular instant in time, if I am given this, suppose I have to be given that, right? So now how will I approach this? I am not going to worry about having to specify this. So what would be T prime? Let me just erase this. If I am now looking at the same problem, so I am specifying at a given point in space and at a given time, I am going to specify an infinite number of normals again, right? So all I am saying is that now if I give us the input, the T of xt, now the stress vector is simply n prime dot t. The stress vector for this would be n double prime dot t, right? And this would be n triple prime dot t, and so on. So all I need to give is the orientation of the surface, and I can tell you what the stress vector is, and I can go and calculate the contact force. It simplifies the problem of having to specify an infinite number of stress vectors at a given point, the Cauchy's theorem. This is in fact probably the most important result in all of this course, actually. This whole development of proposing a stress vector that is dependent on the normal and not aiming it at that, because in the special case of a hydrostatics or a perfect fluid, it is already resolved. It is just an assumption actually. It's not going to hold for fluids in motion. For fluids in motion, we are generalizing it. But just leaving it at this is not helpful. Further resolution of how in the general case the stress vector is dependent on the orientation leads to the final resolution, right? And so what it says is that it reduces the problem of having to specify an infinite number of stress vectors at a given point in order to completely specify the state of stress at that point. It reduces that problem to having to specify just 9 components of a stress tensor from which I can calculate the state of stress at that point, any given orientation of a surface passing through that point. Are there any questions?
But even after resolving this, the fact remains that at a particular point, depending upon the orientation, stress
Exactly.
vector will
Yeah, but
change.
for that, yeah, that is true.
Stress vector will change.
Yeah, it will change, definitely. It will change.
For Cartesian coordinates, n1 and 2 would be xyz. For polar, it would be.
No, that is different. I am being only Cartesian coordinates here. How this whole dot product will translate. Curvilinear coordinates, that's another problem. Right? So first of all, that's important you brought it up, because for the first part, now we erase all of this. Even if you didn't understand a single thing of what I have covered so far, it's still okay. Not too bad, because none of this, I mean, some of this is conceptual and very difficult to explain. I have my own limitations in explaining this, right? If you want to read further on the historical aspects, or did you hand out that? Did you hand out that sheet?
No, sir.
You haven't. What is the point of giving it? Yeah. Okay, no, that, yeah, you can continue with your job. Can you just take a sheet distribute. I hope there are enough copies. If there are not, we'll get more copies. Right? So anyway, you can at least share a copy with someone, and made about 75 copies. I hope there are enough. So if you look at the first reference, that will give more detail. I can write it here. It is by Truesdell, Essays in the History of Mechanics. So if you are able to get hold of that book, you can go through more details on the historical aspect, but it's not really directly relevant. I wouldn't say relevant, it's not going to come, I'm not going to ask any questions on the history in the quizzes, for instance, or the test, right? It is more for motivation and introduction. So if you haven't understood all aspects of what we have covered clearly, that is partly because it's somewhat difficult to explain, partly because I have not carried out all the derivations in great detail. From now on, right, let's start now with a clean slate, a clean board. From now on though, you have to understand pretty much every step of what we are going to cover. So from now we'll start with the actual contents of the course, and we'll be covering some of these aspects in more detail. Some of these equations will be explaining and writing down in proper context. Hopefully you will understand them better. So the starting point here, so let's the starting point is this transformation that I talked about. It's very important to understand the meaning of this transformation, what it means, right? So we said we want to follow the motion of a body, right? I need to follow the motion of every point within that body. So I will freeze the body at some reference configuration, right? And find out, identify the position. Now I'll take a Cartesian, rectilinear Cartesian coordinate. So origin is here. I call the axes will be 1, 2, and 3 rather than x, y, and z. Right? So to give an identity to the body, I freeze the body at a particular reference configuration and choose the coordinates of every point in that body, right, as with respect to a fixed coordinate system, let's say. So the psi with the vector sign means it is psi 1. These are the components. I'll put transpose because I will commonly be writing vectors in a column form. It's the most common way of it. If I write it in row form, I put a transpose to indicate that, right? So that is what it is. So now, this is the body as a whole. So if I'm able to find out what, so the question that this answers is, what is, so this is like a reference configuration, what is the position that this particular point in the fluid, which has coordinates psi 1, psi 2 and psi 3, what is the position it will occupy at a later time t, right? Now we move to a time t, the body itself is moving, but I am not focusing on one particular point, because if I can map each and every material point to its coordinates at time t, I will map the body as a whole to its position at time t. So this is now x, which is x1, x2, x3 at time t. So what describes this motion is this transformation, which is written in vector form. It's actually a vector function of a vector variable. We have 4 variables here on top of psi 1, psi 2 and psi 3 is time. So this is written in full form. It will be x1 is equal to some function x2 is some function of this x3 so important copy. This is a transformation, means it's a function. Right? Normally when I write, I can write y equal to f of of x. This is a scalar function of a scalar variable. So I write y equal to f of x1, x2. This is, you can regard it as a scalar function of a vector variable, because the variables that y depends on is actually more than one. So I can regard it as a vector. Right? If I now consider y1, this is a vector function of a vector variable, because the number of the independent variable is also more than one. The dependent variable is also more than one. So I can write it compactly as y equal to f of x. That's exactly what I've written here. X. I'm writing using the same notation to the function. If you want, I can put a cap. So what this means is that the position of a material point or of a fluid point that occupies a position psi at some reference configuration, what would be its position at time t? That is given by this. If we assume that such a mapping actually exists, the transformation exists, important property of this transformation or mapping is that it is invertible. What this means is that a given function, we say a single value. Whenever we say y is a function of x, it is assumed that y is a single valued function of x. Right? That is assumed. I don't have to say it. What it means is that for every value of x, there is only one and only one value of y. That's what we normally mean by a function. But the converse need not be true. I can now ask, does the inverse exist? That means, can x be written as a function of y? It would mean that for every value of y also there is a single value of x. That need not always be true. This is a classic example of an invertible function is simply y equal to let's say 2x. This is invertible. Every value of x, I have one value of y, I can easily invert it explicitly, and I now know that for every value of y also there is a single value of x. Then I say that this function is invertible. Right? Now, a contrary example is y equal to x squared. So every value of x is a single value of y. But converse is not true. Every value of y, the more than one value of x, so the function is not invertible. That means x cannot be written as a single valued function of y. Right? So this is better, it's easily seen graphically. By plotting this, y equal to 2x would look like this. Right? So clearly you can verify it is a function. But every value of x is only one, intersecting only at one point. But the converse is for every value of y, is there a single value of x is drawn by drawing horizontal lines. Right? That is true for y equal to 2x. If I consider y equal to x squared, this is y equal to 2x. Every value of x, certainly there is only one value of y. Every value of y, there are actually two values of x. So the function is not inverted. So when I say that this is now a vector function of a vector variable, that means that when you're writing it in this way, right, means for every material point which occupies psi, I can find a unique value. It's going to occupy in one position at the time t. By the same token, I can also invert back, and if I tell that this is the position occupied by the material point, by some material, some fluid element at time t, I can go back and find what position it would have occupied at the reference time t naught. That's also unique. We do not have two values, so that's very important. We want to follow the motion in an unambiguous manner. More than one value, then you cannot identify a material point with its material coordinate, more than one can correspond to the same position, then the whole picture would collapse. It's very important for this mapping to be invertible, and that's very important for many of the results that we would derive. So I can also write sine as some function of x and t. That's what is meant by invertibility. So there's a condition for invertibility that we'll explain in the next class. If we stop now, we run out of time. Are there any questions? Okay, if not, I guess there will be no class tomorrow as for A's law. Thursday is a holiday. We'll meet on Friday for the next class.